The first artillery shell that exploded above Obergefreiter Hans Müller's bunker near Bastogne on December 20th, 1944, detonated with precision that seemed to mock the laws of ballistics and military engineering. The Wehrmacht veteran, who had survived 3 years of Eastern Front combat, watched in horror as American artillery rounds burst in perfect airbursts without requiring direct hits or timed fuses, creating devastating fragmentation patterns that rendered German defensive positions useless. "How do they know exactly when to explode?" Müller shouted to his squad leader over the screaming shrapnel that filled the air above their foxholes. "The shells are bursting at the perfect height every single time. This is impossible with conventional artillery." These were battle-hardened German soldiers who understood artillery warfare through years of combat experience on multiple fronts. They had mastered defensive techniques against conventional shells, calculated firing trajectories, and developed countermeasures that had protected them from Russian, British, and American artillery throughout the war. They had no way of knowing they were facing the most revolutionary artillery technology in military history, or that American proximity fuses would fundamentally change the mathematics of artillery warfare through scientific innovation that rendered traditional defensive tactics completely obsolete. Generaloberst Hasso von Manteuffel adjusted his field glasses as his 5th Panzer Army prepared for Operation Wacht am Rhein, Hitler's desperate gamble to split Allied forces through the Ardennes forest and recapture the port of Antwerp. The German commander felt confident that winter weather, surprise, and concentrated armor would overwhelm American defensive positions before enemy reinforcements could respond effectively. The German artillery doctrine that supported the Bulge offensive emphasized massed battery fire, accurate range finding, and systematic bombardment that had proven effective throughout the war. Wehrmacht gunners possessed extensive combat experience and technical competence that enabled precise target engagement using time-delayed fuses and direct-fire missions against American positions. Intelligence reports about American artillery capabilities suggested conventional weapons systems similar to German equipment, with standard high-explosive shells, time fuses, and contact detonators that required direct hits or accurate timing for maximum effectiveness. German defensive planning assumed traditional artillery limitations that enabled effective countermeasures through dispersal and fortification. The tactical preparations that German forces implemented included camouflaged positions, reinforced bunkers, and systematic defensive planning designed to minimize casualties from conventional artillery bombardment. Wehrmacht engineers had perfected defensive techniques that reduced vulnerability to traditional shell fragments and blast effects. Obergefreiter Hans Müller's combat experience included survival of massive Soviet artillery barrages on the Eastern Front, where he had learned defensive techniques that provided protection against conventional high-explosive shells. His confidence in German defensive methods reflected successful application during previous combat operations against experienced enemy artillery. The weather conditions that favored German offensive operations included heavy cloud cover that limited Allied air support while providing concealment for artillery positions and troop movements. December weather in the Ardennes seemed to eliminate American advantages in tactical aviation and aerial reconnaissance. Strategic planning for the offensive assumed American artillery would operate according to conventional limitations that German forces understood through extensive combat experience. Wehrmacht tactical doctrine incorporated countermeasures against traditional artillery that had proven effective throughout European warfare. The initial German attacks achieved tactical surprise that overwhelmed American positions through concentrated armor and artillery support that demonstrated Wehrmacht operational competence despite resource limitations. German forces advanced through American defensive lines using proven tactical methods and experienced leadership. Communications interception revealed American artillery coordination that appeared consistent with conventional fire control methods and standard ammunition types. German intelligence detected no unusual artillery procedures or weapon systems that might challenge established defensive techniques. The psychological preparation that German forces underwent emphasized confidence in proven defensive methods and artillery countermeasures that had protected Wehrmacht units throughout the war. Combat veterans felt secure in their understanding of artillery warfare and defensive tactics. Supply limitations that constrained German operations included ammunition shortages and fuel restrictions that required efficient artillery employment and careful resource allocation. Wehrmacht forces operated under constraints that emphasized tactical excellence over material abundance. The terrain advantages that Ardennes geography provided included natural cover, defensive positions, and concealment opportunities that enhanced traditional defensive techniques against conventional artillery bombardment. German forces felt confident that geography supported their defensive preparations. Medical preparations for the offensive included field hospitals and casualty evacuation procedures designed for traditional combat injuries from conventional weapons. German medical personnel expected wound patterns consistent with previous artillery experiences. The winter offensive was beginning with German confidence in traditional military methods that would soon face technological innovation beyond any European combat experience or defensive preparation. Dr. Merle Tuve stood in the Applied Physics Laboratory at Johns Hopkins University, examining the miniaturized radar components that would soon revolutionize artillery warfare through proximity fuse technology that seemed impossible according to traditional engineering limitations. The American physicist had solved the problem of creating radio equipment small enough to fit inside artillery shells, while robust enough to survive gun barrel acceleration and atmospheric flight. The proximity fuse development that American scientists achieved represented breakthrough technology that combined radar detection, miniature electronics, and precise timing mechanisms in devices smaller than a cigarette pack. These revolutionary components could detect targets and detonate shells at optimal distances for maximum fragmentation effectiveness. Engineering challenges that proximity fuse creation required included designing radio equipment that could withstand 20,000 G-forces during gunfiring, while maintaining electronic functionality throughout ballistic flight trajectories. American engineers solved problems that European technology had considered impossible through systematic innovation and scientific collaboration. The manufacturing process that enabled proximity fuse production included precision component assembly, quality control testing, and mass production techniques that created thousands of units monthly while maintaining reliability standards exceeding 95% effectiveness rates. American industrial capabilities supported revolutionary technology through systematic organization. Security classification that surrounded proximity fuse development included absolute secrecy requirements that prevented information leakage while enabling field deployment against German forces who remained unaware of technological capabilities that would overwhelm their defensive preparations. Scientific security supported tactical surprise. Testing procedures that validated proximity fuse performance included extensive proving ground evaluation, ballistic testing, and field trials that confirmed effectiveness against various targets while maintaining safety standards for friendly forces. Systematic testing ensured reliable performance under combat conditions. The scientific collaboration that enabled proximity fuse success included coordination between military requirements, academic research, and industrial production that achieved technological breakthrough through democratic cooperation rather than authoritarian control. Competitive innovation accelerated development while maintaining security. Quality assurance procedures ensured proximity fuse reliability through systematic inspection, electronic testing, and statistical quality control that achieved performance standards exceeding traditional ammunition while enabling mass production. Scientific manufacturing methods supported technological superiority. Field deployment preparations included training programs for artillery personnel, technical manuals for maintenance procedures, and operational instructions that enabled effective utilization without compromising security. American forces received technological advantages through systematic preparation. The economic efficiency that proximity fuse production achieved included cost reduction through volume manufacturing while maintaining performance superiority over conventional ammunition. Technological innovation created tactical advantages through competitive pricing and systematic availability. International cooperation restrictions prevented proximity fuse sharing with allied nations due to security requirements that protected technological advantages while maintaining American control over revolutionary capabilities. Democratic allies received other forms of military assistance, while proximity fuses remained exclusively American. Strategic implications of proximity fuse deployment included artillery effectiveness that would overwhelm German defensive capabilities through technological superiority rather than numerical advantages. Scientific innovation would achieve tactical dominance through systematic application of advanced technology. The invisibility of proximity fuse technology included radar components that operated beyond German detection capabilities while providing target acquisition that exceeded traditional artillery methods. Enemy forces would face weapons they couldn't understand or counter through conventional defensive techniques. Combat effectiveness testing revealed proximity fuse performance that achieved casualty rates exceeding conventional ammunition by 300 to 500%, while reducing ammunition consumption through improved accuracy and optimal detonation timing. Scientific artillery would revolutionize battlefield effectiveness through technological innovation. The invisible radar was preparing to deliver technological shock that would challenge German understanding of artillery warfare, while demonstrating American scientific capabilities that exceeded European military technology through systematic innovation and democratic scientific collaboration. December 23, 1944. The American artillery response to German offensive operations included proximity-fused shells that began exploding with supernatural accuracy above Wehrmacht positions near Bastogne, creating airburst patterns that seemed to violate fundamental principles of ballistics and military engineering. German forces discovered that American artillery had acquired technological capabilities that rendered traditional defensive tactics completely obsolete. The first proximity fuse detonations that German forces experienced included shell bursts occurring at optimal heights for maximum fragmentation effectiveness, without requiring direct hits or timed fuses. American artillery achieved precision that exceeded human calculation while maintaining consistent performance across thousands of rounds fired. Hans Müller crouched in his foxhole as American shells exploded directly overhead with timing that suggested impossible technological capabilities. The airbursts created fragmentation patterns that reached into defensive positions that conventional artillery could never penetrate through direct fire or timed explosions. The tactical confusion that proximity fuse technology created among German forces included inability to predict shell behavior or develop effective countermeasures against weapons that detected targets and detonated automatically. Traditional defensive techniques proved inadequate against artillery that adjusted explosion timing based on proximity to enemy positions. Combat effectiveness that American proximity fuses achieved included casualty rates that exceeded German expectations by enormous margins, while reducing ammunition expenditure through improved accuracy. Single artillery barrages accomplished destruction that previously required sustained bombardment campaigns using conventional ammunition. The psychological impact on German troops included recognition that American forces possessed technological advantages that challenged fundamental assumptions about artillery warfare. Enemy capabilities exceeded German understanding while creating tactical situations that traditional military training had never addressed. Intelligence analysis that German forces attempted revealed no pattern or timing mechanism that could explain proximity fuse behavior through conventional artillery knowledge. American shells seemed to possess artificial intelligence that enabled optimal detonation timing beyond human capability or mechanical precision. Medical casualties from proximity fuse attacks included wound patterns that differed significantly from conventional artillery injuries due to optimal fragmentation dispersal and improved shrapnel effectiveness. German medical personnel observed casualty types that challenged traditional battlefield medicine and wound treatment procedures. The defensive adaptations that German forces attempted included deeper fortification, increased dispersion, and modified tactical positioning that proved ineffective against proximity fuses that detected targets regardless of concealment or protective positioning. Traditional countermeasures failed against technological superiority. Communications interception revealed American artillery coordination that appeared conventional despite technological capabilities that exceeded German understanding. Enemy forces maintained operational security that prevented intelligence gathering about proximity fuse technology while demonstrating systematic technological advantages. The tactical flexibility that proximity fuses provided. American artillery included effective engagement of various target types, terrain features, and defensive positions through adaptive detonation that optimized effectiveness regardless of tactical situation. American gunners achieved consistent results across diverse combat scenarios. Supply implications of proximity fuse technology included reduced ammunition requirements that enhanced logistical efficiency while improving tactical effectiveness. American forces achieved superior results with fewer resources while maintaining technological advantages that German industry could not duplicate. The technological gap that proximity fuses revealed included American scientific capabilities that exceeded German research and development, despite traditional European advantages in engineering and military technology. Democratic innovation had achieved breakthrough technologies through systematic scientific collaboration. Counter-technology efforts that German forces attempted proved unsuccessful due to inability to understand or duplicate American proximity fuse technology within available time and resources. Wehrmacht technical personnel could not develop countermeasures against weapons they could not comprehend. The shells that think were demonstrating American technological superiority that would influence tactical outcomes through scientific innovation rather than numerical advantages or traditional military excellence. January 1945. German intelligence analysis of American artillery effectiveness during the Bulge revealed statistical impossibilities that challenged every assumption about conventional weapons and military logistics. Wehrmacht technical experts documented American artillery achieving casualty rates that exceeded traditional ammunition by margins that suggested technological capabilities beyond European scientific development. Major Wilhelm Richter studied battlefield reports that documented American artillery performance defying mathematical calculation based on conventional weapons knowledge. Enemy shells achieved accuracy and effectiveness that violated established principles of ballistics, while creating tactical results that traditional military planning had never contemplated or prepared for. The statistical analysis that German artillery specialists conducted revealed American effectiveness ratios that exceeded conventional ammunition performance by 400 to 600%, while reducing ammunition consumption through improved accuracy. These mathematical relationships suggested technological advantages that German science could not explain through traditional engineering knowledge. Combat documentation included casualty reports that revealed wound patterns and destruction effectiveness, indicating American shells that detonated at optimal heights for maximum fragmentation dispersal. German medical analysis suggested technological capabilities that achieved perfect airburst timing without human calculation or mechanical complexity. The tactical intelligence that German forces gathered through battlefield observation revealed American artillery that responded to target positioning with precision that exceeded human reaction time or conventional fire control methods. Enemy weapons demonstrated technological capabilities that suggested automated target detection and engagement. Economic calculations performed by German logistics experts indicated American artillery achieving superior tactical results with reduced ammunition expenditure, suggesting technological efficiency that exceeded German industrial capabilities. Enemy forces demonstrated resource advantages through technological innovation rather than material abundance. Technical analysis of recovered American shell fragments revealed electronic components that German engineers could not identify or understand through existing technological knowledge. Enemy ammunition contained technological capabilities that exceeded German scientific development and manufacturing methods. The psychological impact on German artillery personnel included recognition that their conventional weapons faced technological opposition that rendered traditional artillery tactics obsolete. Wehrmacht gunners understood that enemy capabilities exceeded their technological response possibilities. Strategic implications of American technological superiority included artillery advantages that influenced tactical outcomes through scientific innovation rather than numerical superiority or conventional military excellence. Technology had become a decisive factor that exceeded traditional military planning and resource allocation. Research efforts by German technical personnel proved inadequate for understanding or duplicating American proximity fuse technology within available time and industrial resources. Wehrmacht scientific capabilities could not match American technological development, despite traditional German advantages in engineering and military research. The training implications for German forces included recognition that traditional artillery defensive techniques required modification based on technological realities that exceeded conventional military education. Combat experience suggested enemy capabilities that military training had never addressed through standard procedures. Medical analysis revealed casualty patterns that indicated American artillery achieving optimal fragmentation dispersal through technological methods that exceeded conventional ammunition capabilities. German battlefield medicine faced wound types that challenged traditional treatment procedures and medical preparation. Logistical analysis suggested American technological advantages that enabled artillery effectiveness while reducing supply requirements, creating tactical flexibility that exceeded German logistical capabilities. Enemy forces achieved superior results through technological innovation rather than resource abundance. The intelligence value of proximity fuse technology remained limited due to security measures that prevented German understanding of American scientific capabilities. Enemy technological advantages remained mysterious, while creating tactical disadvantages that German forces could not counter through conventional methods. The mathematics of destruction had shifted in favor of American technological superiority that rendered traditional artillery warfare obsolete through scientific innovation that exceeded German scientific development and military technological capabilities. February 1945. As German forces retreated from the Ardennes following their failed offensive, the mathematical certainty of American technological superiority had fundamentally altered Wehrmacht understanding of modern warfare. Proximity-fused technology represented scientific capabilities that exceeded German development, while demonstrating democratic advantages in research and innovation that would influence post-war technological competition. The final accounting of Bulge casualties revealed American artillery effectiveness that had achieved tactical victory through technological innovation rather than numerical superiority or traditional military excellence. Proximity fuses had eliminated German defensive advantages while demonstrating scientific warfare that exceeded conventional military planning and tactical preparation. Hans Müller survived the Bulge campaign with profound respect for American technological capabilities that had overwhelmed German defensive positions through scientific innovation. His combat experience included recognition that technological superiority could achieve tactical dominance that traditional military excellence could not match through conventional methods. The strategic lessons that proximity-fused deployment provided included validation of scientific research and technological development as decisive factors in modern warfare. American investment in research and development had created tactical advantages that exceeded traditional military preparation while demonstrating competitive advantages of democratic scientific collaboration. Post-war analysis revealed American technological development that had proceeded through systematic scientific research and competitive innovation, while German military technology remained constrained by resource limitations and authoritarian control. Democratic scientific methods had achieved breakthrough technologies through collaborative research. The industrial implications of proximity-fused technology included American manufacturing capabilities that could produce sophisticated electronic components while maintaining mass production that supported global military operations. Democratic industrial organization had achieved technological production that exceeded authoritarian alternatives. Educational advantages that enabled American technological success included university research, scientific collaboration, and competitive academic environments that encouraged innovation rather than ideological conformity. Democratic educational systems had produced scientific capabilities that exceeded traditional European methods. International recognition of American technological leadership included Allied appreciation for scientific capabilities that enhanced collective military effectiveness while demonstrating competitive advantages of democratic research and development. Scientific cooperation had strengthened alliance systems through technological sharing. The economic efficiency that proximity-fused technology achieved included tactical effectiveness that reduced ammunition consumption while improving artillery performance. Scientific innovation had created cost advantages through technological improvement rather than resource abundance or conventional manufacturing methods. Research and development implications included validation of American scientific methods that emphasized competitive innovation and collaborative research over traditional approaches that relied on individual expertise or hierarchical control. Democratic science had achieved technological breakthroughs through systematic organization. The security implications of proximity-fused technology included American ability to maintain technological advantages through scientific secrecy while deploying revolutionary capabilities that exceeded enemy countermeasure possibilities. Technological superiority had created strategic advantages through scientific innovation. Quality control achievements in proximity-fused production had demonstrated American manufacturing capabilities that maintained technological reliability while enabling mass production. Scientific manufacturing methods had achieved technological excellence through systematic quality assurance and competitive production methods. The technological gap that proximity fuses revealed included American scientific capabilities that would influence post-war competition and international relationships through technological leadership. Scientific superiority had become strategic advantage that would reshape global technological development. The workforce development that enabled proximity fuse success had demonstrated advantages of democratic education and scientific training that produced human capital capable of technological breakthrough. Educational systems had created scientific capabilities through competitive academic development. The technological turning point at the Bulge had demonstrated American scientific superiority that would influence global technology development for decades, proving that democratic innovation could achieve decisive advantages through systematic research and competitive scientific collaboration. If this incredible story of how American technological innovation overwhelmed German forces through scientific superiority amazed you, make sure to subscribe to our channel for more untold tales of technology changing warfare forever.